suspected, so I just asked him if he would like to do it, and he replied immediately, "Yeah, I would love to do that."
He likes that because when you're young, you need to do all this as many talks as possible, and then, but he's probably not the best timing in the world. Okay. Okay, great. Now we're on the other side. I'm going to share the thing. Sorry, I usually know what I'm doing most of the time. Okay. Well, I think, do you guys see this? No, you see the wrong one, don't you? Swap this, please. Do you see that now, the correct one?
Yes.
Okay. Well, hello, everybody. Welcome back to the second online SPICE SPIN+X seminars of this fall that I organized here together with Louis Mekiel, Angela Wittmann, and Karen Everso-Sitten, now in Duisburg, but still part of the SPICE advisory team, together with the Collaborative Research Center of SPIN+X that is led by Martina Schliemann, Burkhard Hillebrands, Matthias Chloe. As you guys know, all of you are familiar, this is a webinar, meaning that you see the speaker speak and you don't see the rest of the participants, but you please feel welcome to put in the chat or raise your hands for questions. We have today Felix Casanova giving the next talk. Felix is in the Basque Country, and he's a Iker Basque research professor at CIC in Anagune, in a very nice place where everybody usually tends to like to go to eat lots of food. He graduated from the University of Barcelona in 2004, and he researched a lot of Spintronics materials, magnetic insulators, 2D materials, and now some work on Twistronics these systems. So with that, I'm going to let Felix, who I'm always envious of his perfect last name, to start the talk, and we're looking forward to your talk.
Okay. Thank you, Jairo, for the nice introduction. Can you hear me well?
Yeah, we can hear you very well. Yeah.
Excellent. And I'm going to put full screen on my presentation. Okay, good. Can you see well the screen?
Yes, we can.
Excellent. Okay, so thank you, Jairo, again for the introduction, and thanks everybody for attending to this online seminar. Okay, I'm very happy to give a talk here because that's been a very successful series, right? And then to be able to be part of it, it's actually I'm proud of it. So I'm very happy. But before starting with my talk, in which I will focus on low symmetry materials, on how we can do Spintronics, that is Spintronics talk, right? Using low symmetry materials. First, let me introduce briefly my place. Okay, Jairo mentioned it's a nice city. This is San Sebastian in the north of Spain, in the Basque Country. Okay, we have a nice beach here, and our institute, Nanogune, is located close to the city center. Is this building here? In the institute, our group is called the Nano Devices Group. Currently, we are around 30 people, and it's led by my colleague Luis Hueso here in the middle, and by myself. Okay. Now, this is Spintronics seminar, and I think that I'm not going to be very original here, but I'm going to start showing Moore's law. Probably everybody knows what Moore's law is, right? The number of transistors in electronic, integrated circuits have been doubling every 2 years for the last 50 years. That's a very successful story, and we all know about this. But I would like to point out this is not the only important parameter, the number of transistors in an integrated circuit. There are other important parameters. For instance, the speed of your transistor, what's called the frequency. For many years, this was also increasing similarly to the Moore's law, but for many years now, since 2005, this speed has been limited to a maximum value of 2-3 gigahertz. And the reason is that the heat dissipation, if you go faster, it cannot be easily cooled down. Okay, this limits the total power of an integrated circuit to around 200 watts. Okay, this already tells you one of the problems nowadays, which is energy consumption, right? How power hungry are integrated circuits. Okay, and this gives other problems. For instance, that we are using in general information and communication technologies are taking up a big portion of the total electricity worldwide. Currently, we're around 8% of all the electricity spent, and a big portion are data centers. The estimation for 2030 can be that up to 30% of the electricity will be spent in information and communication technology. Now, probably when this estimation was done, we're not even taking into account the emergence of artificial intelligence, which is also very power hungry, right? So after this introduction, then when Spintronics people like us, jump in and say, okay, we can solve this problem, we can save the world with our spins, right? And a bit the reason for saying this is that there are proposals in which you can integrate memory in the form of magnetic elements, so information can be non-volatile, while you play with this information that's stored, taking it in and out with spin currents that carry the information, and then you can do a logic, you can process this information. Okay, this in principle should increase the speed and decrease the power operation. Indeed, for several years, there's been these different spin-based logic proposals. Maybe one of the first one was this magnetologic gate by Hananderi and co-workers. Here, the basic idea is that your information is stored in 4 ferromagnetic electrodes, like 2 of them contain the inputs, 2 of them the operation you want to perform, and you use the 5th ferromagnetic electrode to read out information. And basically, they are all connected with a channel in which you can transport your spin current, and the spins diffuse and mix, and that's how the operation is performed. Here you can rewrite the magnetic element by charge current, applying a spin transfer torque effect. Some variations of this original idea may be found, for instance, in this all-spin logic concept, which also is quite well known. The idea is exactly the same. Probably the main difference is that even the writing is done via the spin transfer torque. To write the magnetic element is done with pure spin currents. But the main problem of these approaches is that energetically actually are not that favorable, because you need, at the end, you need currents to switch to write, and this is not very energetically favorable. Also, the operation is done by diffusion of spin current, so they have to travel, and the spin current is not conservative, right? So it decays exponentially. You need to drive a lot of spins so that some of the spins survive long enough. For some of these reasons, more recently, researchers at Intel did this proposal of a magnetoelectric spin orbit logic. The basic idea is similar, so the information is still stored in magnetic elements, but now to save energy, the writing, instead of being done through current, is done with voltage, using any magnetoelectric effect. And the information that gets out, that you read the information out of this magnetic element, is done with spin to charge conversion. So now the spin current that carries information is converted into a charge current. So the interconnect between different elements is not done with pure spin current, but actually with charges. Okay. These in principle have a much better energy efficiency. Now, a key element here for doing this spin to charge conversion is different phenomena. For instance, spin Hall effect. Probably most of the audience will know what spin Hall effects, but for the sake of completitude, I will do a reminder. This occurs in materials with a strong spin orbit coupling, right? When you pass a charge current due to spin-dependent scattering, you separate spins up to one direction, spins down in the opposite direction, so you get a transverse spin current. So this can be used to generate the spin currents without the use of a magnetic material. This effect follows the right-hand rule. Okay, so the spin polarization, the charge current, and the spin current have to be orthogonal to each other, and the efficiency is given by this parameter theta, the spin Hall angle. Okay, although I will show later that that's not the only relevant parameter here. You also have the reciprocal effect, right? If you apply a pure spin current in your system with strong spin orbit coupling due to the same spin-dependent scattering, you will create a transverse charge current. So you can use these to detect spin currents. And actually, spin Hall effect has been crucial to discover many new spin-dependent phenomena, like spin-Seebeck effect, spin pumping, spin Hall magnetic resistance, or many more. But also has a lot of interest for applications. For instance, in magnetic RAM memories, now it's trying to be applied via spin orbit torques. So the charge to spin conversion is used to write, to switch a magnetic element, right? And this is actually very close to be commercial, okay? And on the other hand, you have again the reciprocal effect, right? Instead of using the direct effect to write a magnetic element, you can use the inverse effect, the inverse spin Hall effect, to read a magnetic element, which is the idea of this meso proposal of Intel. Although this is just a proposal, this is close to commercialization. But in order to see if this could really be the case, this reading part, magnetic readout for the meso logic, it's actually quite demanding. If the device ever will work, we need to get voltage outputs of around 100 millivolts. It's quite high because you need them, then this voltage will be used to write the next memory element, okay? So to study if this is feasible, we did some very simple devices. This was a collaboration some years ago with Intel, in which we fabricated a very simple device. This is a ferromagnet, cobalt iron, and this is just a transverse wire of platinum. This is a prototypical spin Hall material, but it's in a T-shape, so we can pass current from one to the other and measure a transverse voltage, okay? When you inject your spins from the ferromagnet into the spin orbit material, they will deflect to the right or to the left, depending if the magnetization is pointing in one direction or the other, and the voltage should change sign, okay? We typically normalize this voltage to the injected current because this is a linear effect. So if we apply 100 microamps, which is a reasonable current, then it means that this transverse resistance has to be around 1 kilo ohm, okay? When we did this experiment, we switched with an external magnetic field, this ferromagnet, we indeed could observe the two magnetic states, okay? So indeed we can use the inverse spin Hall effect to read the magnetic state. However, the signal that we get, it's not 1 kilo ohm, it's much smaller, 10 milliohm. So we are really far away from the requirements. We could see by applying a simple one-dimensional spin diffusion equation, which are the parameters to enhance this signal. Actually, many of these parameters are just dimensions. Essentially, when you make this device smaller, the signal goes up, which is a good thing. We were able to increase almost 2 orders of magnitude this signal just by shrinking. But what I want to point out here is that there is a more fundamental limitation here, which is that the conversion efficiency of this spin-to-charge conversion is governed not only by the spin Hall angle, but by the product of the spin Hall angle and the spin diffusion length of the material, of the active material. The spin diffusion length, as you may know, is the distance at which a spin current will decay before it's lost, right? And this enters as the product. The problem with simple materials like metals is that to get a long spin diffusion length, you need weak spin orbit coupling. While if you want a strong spin Hall angle, you need strong spin orbit coupling. So this is obviously mutually exclusive. If we look at the example of the prototypical platinum material, we know that the spin relaxation mechanisms are dominated by the Elliott effect. So this means that the spin diffusion length is inversely proportional to the resistivity of the metal, while the spin Hall angle is typically at the intrinsic regime, because spattered platinum typically is moderately dirty. This means that the spin Hall angle is proportional to the resistivity. So you don't need to do rocket science to see that the product theta lambda will be a constant in this case, and there is nothing you can do about it. So it's limited. And actually the value is relatively low. So unless we change completely the physics of the materials, we are not going to get these very large required voltages in spin-to-charge conversion. This is the example case of meso, but other potential applications where spin-to-charge conversion may be necessary also has this limitation of the product between theta and lambda. Okay, so this was my long introduction, and Now, what I want to show is that there are other materials that can try to improve these effects, and one are 2D materials. 2D materials have intrinsically a low symmetry. Okay, so in the first part of the talk where I show results, I will show van der Waals heterostructures. We'll see how different they will behave from metals. I will also show then how we can go and get more effects by breaking symmetries here, and the symmetry we will break it by twisting the angle between in the van der Waals heterostructure. In this case will be graphene and 2D material, a transition metal decalcogenide. And in the second part, which will be at the end shorter, we will see how materials, bulk materials that intrinsically have low symmetry, can also give very interesting effects in spintronics. In this case, I will be talking about chiral tellurium. Okay, so we start with the first part. Graphene is the prototypical 2D material, and in spintronics is well known because of the weak spin-orbit coupling, right? This gives rise to very long spin diffusion lengths, even at room temperature. Values up to 30 microns have been reported, properly fabricating the device. But what's interesting of a spintronics is you can also enhance the spin-orbit coupling with different strategies. For instance, by hydrogenation, by atomic decoration of heavy atoms on top of the graphene, or by proximity with another 2D materials. Okay, that's what I'm interested in here in this talk. One of these interesting 2D materials are transition metal decalcogenides. There is a subclass of these materials like molybdenum disulfide and tungsten diselenide, which are semiconductors, but they have two interesting properties for spintronics. One is a strong spin-orbit coupling. This gives rise to a giant spin splitting, especially at the valence band. But they also have broken inversion symmetry in the plane, which gives rise to inequivalent valleys, K and K prime here, or minus KK. And because of time reversal symmetry, the spin splitting has to be opposite in the two valleys. This gives rise to this effect called spin valley locking, right? So essentially, the low energy state in one valley is spins up, and in the other valley it spins down. Okay, so there is a locking between valley and spin. This is sometimes also called Valley-Zeeman coupling. Okay, so these are very interesting properties for spintronics. But if you want to do electrical devices, electrical spintronic devices, it's very challenging to inject spins electrically in semiconductors. That's been, tried for many years, and it's not easy. But we can do a trick here. We can combine this TMD with graphene, and some of these properties will be imprinted in graphene by proximity. So this has been, theoretically demonstrated how this spin texture with spins out of plane have opposite direction for one valley, and in the other valley in graphene itself. Okay, this Valley-Zeeman coupling appears. And also because it's a van der Waals heterostructure and you break out of plane inversion symmetry, you also have a Rashba effect appearing there, right? This extra spin orbit couplings in graphene give rise to phenomena that can be observed experimentally. For instance, weak anti-localization has been observed in graphene itself. These are experiments that show it. Anisotropic spin relaxation. Spins in plane will relax faster than spins out of plane because they are protected by this out of plane spin texture. This has been also observed, experimentally demonstrated. And then regarding a spin to charge conversion, which is what we are interested in this talk, we've also observed the effect appearing. We have two effects, the spin Hall effect that I already introduced. This we observed for the first time like some years ago, and also our colleagues in Barcelona, the group of Sergio Valenzuela, and also the Rashba-Edelstein effect, which is another effect that converts spin current into charge current, and I will actually explain it a bit later. And this was also demonstrated by our colleagues in Groningen and in Barcelona. Okay, so this is a bit of a spoiler, but the idea here was that if this Valley-Zeeman coupling that have spins out of plane could induce spin Hall effects, and some years ago theoreticians in Barcelona, the group of Stefan Roche, predicted that they should have it in the absence of inter-valley scattering, and the spin Hall angle expected could be quite large. They calculated values up to 4%. Okay, In the theory, they also see how the spin Hall effect, the spin Hall angle, or more precisely the spin Hall conductivity, could even change sign when you move the Fermi energy position in graphene from, the Hall side to the electron side. So this could be very interesting as well. In order to confirm this prediction, we designed a device which consists of a cross of graphene, where just the junction of graphene has the TMD material on top. So only the middle region is proximitized by the TMD. Then we used a well-known technique in Spintronics in graphene, which is called a non-local spin valve or non-local technique, which we use a ferromagnet to inject spins using a current that flows in this loop. This creates accumulation of spins at the graphene, and it diffuses in all directions. So on this side, even if there is no current, you have a pure spin current flowing. So then we expect that at the junction, you will have a spin to charge conversion, so you should measure some voltage. Okay. This, because the current and the spins are separated, you avoid spurious effects. So it's a reliable method. But we have a small problem here. If you remember the right-hand rule, in the case of graphene, the spins have to be out of plane in spin Hall effect. But we typically, have in-plane magnets, so we inject spins in plane. The trick we will do to bring the spin from in-plane to out of plane is to induce a precession. So we can apply a magnetic field perpendicular to the spins, to the magnetization, but perpendicular to a magnet, but in the plane. So spins, when they diffuse, they will precess and eventually be out of plane at the junction. And if this happens, then we will see a non-local voltage. So we expect something like this with a maximum at certain magnetic field, then it will disappear because of the diffusion. If you apply the magnetic field in the opposite direction, the precession, makes the spins pointing down, not up, and then the spin to charge conversion is the opposite. So you get an antisymmetric curve. That's what you expect. This is called antisymmetric Hanle curve or antisymmetric precession curve. But you can do even something else to check you are doing it right, which is to change the initial magnetization of your ferromagnet. So the spins will be in the opposite direction, then everything is inverted, and the curve will show something like this. Okay, so this, if we observe something like this, this would be the signature that we have spin Hall effect in our graphene. Okay, so that's what we try to do experimentally. Here we have a graphene which is etched in a cross shape. This is a reference graphene, and this is a graphene where molybdenum disulfide is placed on top. And then we have cobalt electrodes where we can inject the spins. We do the experiment, the configuration that I discussed now, and if we do it in the reference graphene, we only have a linear background. But if we do the experiment on the proximitized graphene, we see this antisymmetric curve that I expected. We can now switch the cobalt injector, and the curve switches while nothing happens at the reference, right? So this was actually the first demonstration back in 2019 that spin Hall effect could occur in graphene itself by proximity. What's interesting now is we can remove the background by subtracting the two curves. We can get a clean signal, and we can adjust this signal to a one-dimensional spin diffusion equation and extract the relevant parameters here. The relevant parameters are the spin Hall angle of our graphene. We got a value of 4.5%. This is remarkable. It's similar to platinum. And a spin diffusion length, which has been reduced with respect to pristine graphene. Typically, our graphene, which is not optimized, have 1 to 2 microns, pristine graphene. Here it's reduced, of course, but still much, much longer than heavy metals like platinum, right? So if we look at the relevant figure of merit, which is the product of theta and lambda, we get up to 13.5 nanometers, which is 2 orders of magnitude better than platinum, okay? At room temperature, it decays almost 1 order of magnitude in this case, but still is 1 order better than platinum, okay? So now, because the physics here is different from single metals, we can have a combination of a long spin transport and large spin Hall effect in the very same material. We did some follow-up experiments. Also, some colleagues, now for lack of space, I will not show them, but I will mention them. We tried it with tungsten diselenite. In principle, it has a stronger spin-orbit coupling, so we expected larger signals, and indeed we observed larger signals. We also did a gate dependence that we could not do in this first experiment, and we see that the signal can be strongly modulated by the backgate. Unfortunately, we could not see the predicted sign change, but this, I can mention, was something observed by our colleagues in Barcelona, the group of Sergio Valenzuela, the reference I mentioned before. So what's interesting in this material is that we got a very large, even larger efficiency. So in these conditions at 100 K and certain gate, the product was up to 40 nanometers. So this was very, very big. So what's interesting in these van der Waals heterostructures is that on one hand, we have a gate tunability of the spin Hall effect. This is something, of course, you cannot do with metals. And one of the largest efficiencies reported for spin to charge conversion. Okay, so these are very interesting systems. No. The second phenomenon where you can do spin to charge conversion that I mentioned is the Rice-Weilstein effect. This occurs in systems with broken inversion symmetry, typically in 2D systems, but necessarily, for like interfaces, for instance. In this case, due to the spin texture that you get to the broken inversion symmetry, when you apply a charge current, this charge current is spin polarized. So you get spin accumulation, and then this spin accumulation can diffuse away from the system. It can be into the third dimension, if it's an interface, for instance, or if it's a 2D system or two-dimensional electron gas, for instance, it goes away in the same in the 2 dimensions, right, in the same plane. You also have the reciprocal effect, again, the inverse Edelstein effect, which you can inject a pure spin current that allows to accumulate spins in your system from the third dimension, or it's a 2D system in the same in the same plane, and this induce a net charge current. Okay, so here the figure of merit, because you go from a 3D spin current into a 2D charge current, has unit of length. So this Edelstein length is actually the equivalent of the product of theta and lambda that I mentioned before for the spin Hall effect. Or if it's a purely 2D system, then it's a dimensionless parameter, and that has the same role as the spin Hall angle. Now the question is, if in these van der Waals heterostructures that you have Ricebach coupling, if you also have Rice-Weilstein effect? The answer again is that theoretically, yes, it was predicted by different groups. Here we have the work of Afidani et al. And Garcia et al. And you also see how, depending on the Fermi energy position in the graphene, you can also change the sign, okay, of the effect. This is the theory, and then experimentally, I mentioned it before, it was also demonstrated by different groups, by the group of Van West in Groningen and the group of Valenzuela in Barcelona. Okay, but now what I want to show is to go a bit beyond this, because so far I've been neglecting one parameter here, which is the twist angle in this heterostructure between the graphene and the TMD. Okay, but now there are different theories, and I will mention this one, our colleagues of Tony Law in Minnesota, in which this typical spin texture that you get in Ricebach systems, where the spins are perpendicular to the momentum, occur because you have some mirror planes in your system, and this actually only occurs between when your graphene and the TMD are one on top of each other at certain angles, at 0 and 30 degrees. But in any angle in between, mirror symmetry is broken, and then the expected spin texture in your system has a radial component now. Okay, so you don't have only the tangential component of the spin, but also a radial component. And you can quantify this by defining the so-called Ricebach angle, which could be the angle which is a departure from the from the tangent. Okay. This Ricebach angle actually can have very different values in between a twist angle of 0 and 30 degrees, which they have to be strictly 0. The Ricebach angle can oscillate between negative, positive values and negative again. Seems very, very complicated shape. But now what happens with this heterostructure that we have is that regarding spin-to-charge conversion, you have three different components. First, you have the spin Hall effect. Okay, so you can create spins out of plane, and this is something we already showed before. We demonstrated it. You can have the Reich-Weidelstein effect, so the spins are in plane but perpendicular to the current, X spins, which it was already demonstrated. But now, because of this radial component that appears, you can have an unconventional Reich-Weidelstein effect where the spins are actually parallel to the current, Y spins. So you can have spin-to-charge conversion in all three directions. Okay, so this is what we wanted to confirm. Okay, and this would occur because of the broken mirror symmetry, the twisted heterostructure. So now I come back to the experiments that I was showing before, because I want to show you that with this exact the same measurement, we can detect not only the out-of-plane spins, which is this signature. If we see this signature, I say this is spin Hall effect in the graphene, but we can also measure X spins being converted, because when you apply the magnetic field, if it's strong enough, you pull the ferromagnet in the hard axis, so you are injecting X spins. If there is this conversion, then you expect a signal like this that saturates eventually. If you apply the magnetic field in the opposite direction, you saturate in the opposite direction, and you have an antisymmetric curve. But in this case, if you change the initial magnetization, that doesn't matter, and the curve is the same. So if you observe something like this, it means you are converting X spins. But you can also check, and of course, if you see this, it's because it's the Reich-Weidelstein effect in the proximitized graphene. Okay. You can also have spins in the Y direction being detected, if there is any, because actually at zero magnetic field, you are injecting the spins in the Y direction. Okay, and if there is a conversion, you will detect them. So you will get a detection at zero magnetic field, but then when you pull towards the X direction, the signal will disappear. And in this case, the effect will be symmetric with the magnetic field. Okay. And if you change the initial magnetization, now the signal will reverse sign and the whole curve as well. Okay, so if you observe this signal, this is a signature of Y spins being converted, and this would correspond to this unconventional Reich-Weidelstein effect, where the spin accumulation is with spins parallel to the current. Okay. So, okay, this is what we try to do. How we fabricate the devices, that's one of the most challenging parts, because knowing the twist angle in a heterostructure is not easy, right? Because you have different crystals originally, and you have to know the absolute value of the angle. So quickly, for those which are experimentalists and grow samples, that's fabricate samples, that's how we did it. We exfoliated some tungsten diselenite in a PDMS stamp. So some of the crystals we can identify, they come from the same original crystal, so they have the same orientation. So we can now stamp these crystals on a graphene one time, then rotate our sample and sample holder certain angle, 30 degrees in this case, and stamp again one of these crystals that were originally on the same crystal. So we know that one flake to the other, they have a difference of 30 degrees. Okay. Once these two are identified, we can pattern our graphene. So the two parts of the graphene come from the same flake of graphene, so the orientation is the same. And then we can put our magnetic and non-magnetic contacts to do, the final device. Okay, so the device looks like this. In the very same chip, we have two devices where the tungsten diselenite is twisted in a different angle with one another. Okay, so but what we don't know is the angle between the graphene and each one of these. The way to know it, and this was what we tried to do next, and it was not easy, but our colleagues in Charles University in Prague were successful to do, was to use a second harmonic generation. So it's you shine linearly polarized light laser on your flake. Okay, and then when certain symmetries are broken, you get a second harmonic generation. So at double the frequency, you have a signal, and this is different depending on the orientation or your crystal. So when you rotate your circularly polarized light, on the top of the crystal, in this case in tungsten selenide, we see this this periodicity, which corresponds to the rotation symmetry of our tungsten selenide, and we can identify where is the armchair direction of our flake. And we see it's different for flake 1 and flake 2, while we know the armchair edge of our graphene by Raman spectroscopy. So like this, we can really know the twist angle. In the first device is 37 degrees, and in the second device is 7 degrees. So the difference is 30 degrees, which is what we did experimentally, but now we know the absolute value. Okay. So now in these devices, we do the experiment that I mentioned before, but in this case, I expect an entanglement of different contributions. Okay. So here is the signal, and that looks kind of complicated, but we can disentangle the 3 different component X, Y, and Z spins by doing the difference between the curve with magnetization up and the curve with the magnetization down, or the average. And in this case, we can have 2 effects, the fact that depend on the initial magnetization. These are the Z and the Y component, but I mentioned before that one is antisymmetric and the other one is symmetric with magnetic field, so we can also disentangle it. If we do this process, we see that we see the 3 types of signals in our device. Okay, so if this is the equivalent expected effect here, you know, the 2 curves are already average, so that's why we only see one of them, right? But this is what I expected, and that's what I see. Okay, so we can see this unconventional Rashba-Edelstein effect. Okay, just briefly to mention that all these 3 signals are actually gate tunable. In the case of the Rashba-Edelstein effect and the unconventional Rashba, they can change sign across the charge neutrality point of graphene, which is nice. It was expected. It's not the case of the spin Hall effect. But let's go to the most interesting part here, which is now a comparison with the second device. The second device, if we do the experiment, we see a very different shape already. So now if I disentangle the 3 components of a spin-to-charge conversion, what I see, the first thing I see is that the unconventional Rashba-Edelstein effect has disappeared. It's not present there. Okay, we could mention that, okay, the spin Hall effect seems almost vanished as well. It's true, it's very small in this case, but at different gates, actually, the effect is more clear. So there is spin Hall effect, but of course, will also vary with the twist angle. But let's concentrate now on the Rashba-Edelstein part. So the unconventional has disappeared. Okay. We can go further and make other devices. For instance, I'm showing here a device number 3, in which again, we observe the 3 components. Okay, and now what I want to show you is that this S-shape device that corresponds to the conventional Rashba, okay, is this S-shaped curve that would correspond to this. It has the same sign in both of them. It means that when you apply a charge current, okay, the transverse spins that you generate are like pointing to the right in both cases. Okay, but actually the unconventional Rashba, which is the difference between the 2 curves, you see here that the curves are reversed. If I do the difference and do the symmetrization, actually you see that they are opposite. Okay, so in one case, the spins that you generate are parallel to the current, while the other ones are anti-parallel to the current. In other words, this means that in the first device, you have a spin texture with certain helicity, where the radial component points inwards, but in the other device, the radial component points outside, so the helicity is the opposite. Okay, so we can control actually the sign of the Rashba angle, right? So what we can do actually is to for every device to take the ratio between the Rashba signal and the conventional Rashba signal, because they are like self-calibrating in one device, and get the angle, right? So if we do this, I show 3 devices, but we have 2 more, so total we have 5 devices. We see how the Rashba angle, as a function of the twist angle, can be either 0, it can be negative, or it can be positive. And actually, if we compare to the theoretical prediction that I showed before, this is the gray points, although the absolute value of the angle does not match, the tendency, the change of signs match very well. So here is positive, and the largest value we can get, negative, and the largest value we can get, and then here it gets very small and crosses 0, right? So here within the error, we don't see any signal. So actually we have an excellent agreement with the theory, and this shows how the twist angle can allow us to control the spin texture of these systems, and therefore, turning on and off this unconventional component, or even changing sign. Okay. So now I'm moving to the second part. This will be shorter, which shares something similar here. When you have chiral materials, you also have these low symmetry effects, right? You have a broken inversion symmetry, and you don't have mirror symmetries. Okay. So in general, in nature, there are many chiral compounds. So everybody knows how DNA and sugars are chiral. So you have, different handedness, right hand, left hand, chirality, and this sometimes in the biology gives different properties. But in solid state, we also have some systems like this. And an interesting one is tellurium, which has a trigonal structure, which means that the crystals of tellurium can be right-handed or left-handed. And this will have consequences in spintronics. So I would like to show you this briefly. The crystals we will work were fabricated by hydrothermal solutions. So these are elongated nanowires, which then we can spin coat in a substrate, find one of them, put contacts electrically, and do magnetotransport measurements. I will explain later about the transport measurements. But we can also figure out what chirality this wire has. In fact, this is a bit of a spoiler, because first we do the experiment in the device, and finally we destroy it because we have to do TM to see it. But I'm, for the sake of the story, I will explain it the other way around. So we can, finally cut this wire. This is the wire, and look at the TM. And typically, the wires have this shape, which follows the trigonal structure. But in high resolution, you see these, these triangles. These 3 dots are the 3 atoms of tellurium. Okay, that corresponds to the trigonal structure. These triangles actually are not in the same plane, so they are actually a screw. So that's where you have the right-handed chirality or left-handed. And between the different wires, they are connected by van der Waals interactions. Okay. With this cut, however, we cannot know if this is right-handed or left-handed. Okay. We have actually to do a longitudinal cut here that you can see it's performed here. Okay. Although even if the cut is perfectly vertical in the vertical plane, actually, between the 2 chiralities, you don't see a difference. We see these smiley atoms. We call it smiley in both cases, so you cannot know. But if you tilt your crystal 30 degrees, then you can see a difference in the atomic arrangement for the right-handed and the left-handed. Okay, so this is how we can know unevocally if our tellurium is right-handed or left-handed. So tellurium is interesting because it's spin texture. Okay, this is the band structure calculated by DFT by our colleagues in Halle, by the group of Ingrid Mertig. Everything of interest for transport occurs close to the edge point. That's where you have the band gap. And tellurium is a naturally p-doped semiconductor. Okay, so everything of interest is in the valence band. Okay, there are relatively simple Hamiltonian models that can mimic the valence band. This is a tie banding calculation, and from here at certain cuts, you can see how is the spin texture in tellurium, and interestingly, has a purely radial spin texture. Okay, so in the previous example that had the twist angle, we had the radial component, right? But here you only have the radial component. So all the spins are pointing out, right? And parallel to the momentum. This is for left-handed tellurium, but if you use the right-handed one, actually the spin texture is exactly the opposite. It's pointing inwards, okay? So there is a difference between right-handed and left-handed. Now, if you have this spin texture, you should have the unconventional Rashba-Edelstein effect that I mentioned before, right? You apply a current in the chiral direction, in the Z direction. You have a displacement of the Fermi contour, and then you are accumulating spins parallel to the current. Okay. Here in these devices, we cannot do the experiments that I showed before with graphene and the non-local structures. We're going to do a simpler experiment, which also can probe the Edelstein effect. This experiment is basically doing magnetotransport. So the current is applied along the tellurium wire, and we apply a magnetic field and rotate in the plane. Okay. Typically, in a magnetoresistance experiment like this, you expect that the resistance will be different if the magnetization is, sorry, if the magnetic field is parallel or perpendicular to the current, which is something we observe here. But there is an important feature here, is that when the magnetic field is parallel or anti-parallel to the current, you have different resistance value. Okay, and the reason for this is that this spin accumulation actually acts as an internal field, so it either adds up or it subtracts for the external magnetic field. So the effective resistance of the system is different. Okay, this means that if instead of applying a current in one direction, we apply the current in the opposite direction, we are accumulating the opposite spins, and then the effect is completely reversed, right? So now you see the lower point is with a magnetic field along, the current, and the opposite effect in the opposite current. So the resistance essentially depends on the relative alignment between the current and the magnetic field. This effect actually is known in the literature with different names. It can be called unidirectional magnetoresistance, or some people call it bilinear magnetoresistance, because actually the effect is linear with magnetic field and current. This classically, it's known as magnetochiral anisotropy, or even some people call it non-reciprocal transport. So in the literature now is a bit of a mess, but it all stems from the same effect, right? To get this, this extra component in your system, you have to have broken inversion symmetry, which is the same one that gives you the Reich-Edelstein effect, right? So it's all linked, it's all the same. So this difference between the two current directions actually can be maybe seen better if you do the difference between the two. In other words, for experimentalists, if you do an AC transport experiment, you look at the second harmonic response and you see a signal. Okay, this is equivalent to the second harmonic. And yeah, we have a clear signal when the current is parallel to the magnetic field. So it means you have this radial spin texture. Okay. Now this is for left-handed nanowire. If the nanowire is right-handed, we have exactly the opposite effect. So the difference here, instead of being positive and negative, is now negative and positive. Okay. In other words, we are showing here that the spin polarization actually is opposite with the handness of our wire, right? So the chirality defines the spin polarization. Okay, so we can experimentally observe it and manipulate it. So one last thing here is that we cannot quantify the Reich-Edelstein effect by itself from this experiment, but we can quantify the strength of this unidirectional magnetoresistance. So this is basically the magnetoresistance normalized to the current and the magnetic field because it's linear to it. In our tellurium, this parameter, which these particular units have the value of 10 to the minus 6. If we compare to other systems with broken inversion symmetry, in which they measure the same effect, the signals, the magnetoresistance are 1 order of magnitude smaller or less, meaning that tellurium, has a very, very strong effect on this regard. Okay. So with this, I will be at the end of my seminar. So I show you how we have this spin orbit proximity in van der Waals heterostructures that give a very interesting new physics for spintronics, for instance, gate tunable and very large spin to charge conversion efficiency. We see that breaking symmetries, lowering the symmetries, we can induce new spintronic phenomena, for instance, this unconventional Reich-Edelstein effect. In other words, finally, we can combine Twistronics with Spintronics. And also, I've shown that tellurium is a very nice system, a nice playground for exploring chirality in spintronics, which is something relatively new, but with a lot of interest. Finally, I would like to acknowledge all our collaborators here. the group of Stefan Roche in Barcelona, Fernando de Juan in San Sebastian, the group in Halle led by Ingrid Mertig, the group of Minnesota, Tony Lowe, and also the team in Charles University in Prague for the second harmonic generation measurements. Always the funding, of course, and thank you to you for your attention.
Thank you very much. You can get your applause there from the audience. So wonderful talk. I think we're now open for questions. If you ask questions to Felix, please raise your hand and I will pass along the information. I don't see anybody raising their hands. So I'm going to start a little bit with the reciprocal aspect of these things. Yeah. So now in graphene, you have these non-reciprocal effects and conventional from a combination with this Rashba. In what way does it connect if you put, say, a superconductor on top or use graphene then in these systems as a kind of a junction of, have you thought about this maybe, or?
In a superconductor?
Yeah, essentially the now claims of some non-reciprocal Josephson junction effects with chirality involved in there. You're showing essentially that non-reciprocity in this graphene. How would that change these effects if, for example, you imagine inserting that system in those junctions?
That's a very tricky measurement. A very tricky
maybe theoretical.
Also measurement, right? Yeah. So, I mean, definitely there must be some effects. Actually, there are reports of these non-reciprocal effects in superconductors, even without breaking symmetries, without having chiral structures or anything. And this is something a bit we're actually still trying to understand why a non-reciprocal effects appears in pure superconductors. Actually, there are some papers around. So adding chirality here may even make it even more complicated, right? But honestly, I think maybe a theoretician like you might help understanding this. So
I think it would be interesting. It just came up to me because I was so that's a new result. I wasn't aware of it, and then I'm aware more of the one that had been discussed, like Stewart and these guys discussed. Not the only one observing it, of course, but it could be interesting.
Yes, I mean there are some of these non-reciprocal transport effects, even in superconductors where there is no broken symmetry. So there is something intrinsic from the superconductivity itself. So in this regard, my knowledge of superconductivity is very limited. So I struggle to understand why it's happening actually in these systems as well, and I'm not sure there is a clear picture of why it's happening. Yeah. So
okay. Good to have to look at the reference. Lucas, let's go next with you. If you can mute yourself. Yeah.
Can you hear me?
We can hear you well. Yeah.
I was wondering, you use this moly disulfide or tungsten diselenide. I'm not sure if you mentioned that, but what about metallic TMDCs like 1T materials? I think like platinum ditelluride, palladium ditelluride, or whatever other material. I don't mean specific material. I mean, in general, is the metallicity a problem or not?
Okay, in principle, for symmetries, it's not a problem, and all the effects should also appear there. In fact, we have some experiments also that I didn't mention, for lack of space, with niobium diselenide, for instance, which is a very good metal. It's even superconductor actually at low temperatures, but even in the metal state, the main problem is a bit of interpretation of the results because because these are semiconductors, all the currents and spins flow in the graphene only. If the TMD on top is metallic, then you will have a parallel channel where you can also generate spin currents, because the material itself can have spin Hall effect, or Rashba, Edelstein effect. So you may have components coming from the metal TMD itself that will, add up to whatever is induced in graphene. So then, each component that we detect claim it comes from one effect and not the other, would not be possible experimentally because they may give rise to the same spins in the same direction. So we can know where the spins are generated, right? If they are in which direction. But if there are different sources of these spins, we cannot disentangle. Okay, so this would be the main issue. Let's say that to make sure that that the spins come from this effect and not from another effect. Because they are metallic, you could have effects in the TMD itself.
The tungsten diselenite and moly disulfide are very, I would say, in quotation mark, easy materials. Like, I think they are very clean in a sense. These other ones may be more reactive. Do you think there is a problem of what you have in between, or like impurities in between the layers and things like that?
That's a good question. I mean, in terms of, you mean others, you mean these metallic ones or other semiconductors like
I mean, maybe the other ones like niobium one that you mentioned, maybe it's not as clean, or you don't.
I mean,
don't think this is a problem.
I don't think this is a problem because at the end you have this van der Waals gap right between the graphene and the TMD you put on top. So this would not be the main problem. I could say that the problem itself is in the fact that you have shunting of all your currents through the metallic layer, right? The impurities and defects they probably all have. Actually, one discussion, it's in some of the papers, is that the spin Hall angles that we are actually detecting are quite large. I mentioned 4.5%. The theoretical prediction from the intrinsic effect actually predicts lower values. Usually the things go other way around, right? Theorists predict very large values, and then if you see something as an experimentalist is tiny. This is the other way around. So that's why we suspect that the effect we observe is not only I'm talking about the spin Hall effect. It's not only intrinsic, but it may be some extrinsic contributions, right? Impurities like defects of the sulfur or the selenite might locally have act as scattering centers in the graphene. So it could be like an extrinsic contribution as well. However, experimentally, it's very difficult to distinguish between the intrinsic and extrinsic contributions of spin Hall effect in this graphene. But it seems that if there are impurities, it kind of works in our favor to have larger effects. But this is kind of a guess. We cannot experimentally, we cannot prove it.
Okay, perfect.
Thank you.
Thank you, Alireza. How about you? Next.
Yes, thank you. Do you hear me?
Yes.
Yes, I have only two short questions. One, in your non-local experiment, why you couldn't use autoflame ferromagnet as injector? Okay,
you can use it.
Yes.
If you master PMA, like perpendicular magnetic anisotropy. Experimentally is much more challenging. If you look around at the literature of lateral spin valves, either in graphene or in metals, they are mostly cobalt or permalloy. They are easy to use, and they are in plane. There are a couple of papers where they can do out of plane PMA, but this complicates all the fabrication. And in this case, the trick is easy. We have the easy fabrication of in plane, and then we put a magnetic field and we make the precision.
Yeah, then it's mostly experimental challenge. But
it's just
second
experimentally.
Second question is that do you have any idea that how it looks like the band structure of this bilayer especially when you twist them? Because you always compare your experiment with some Rashba model, but is there any DFT calculation that show that is really
I think so. I mean, there are. I just mentioned this one because I was a collaborator on this work with Tony Low, but there are other works, like the group of Fabian, for instance, the group of Ferreira as well, and others. Sorry if I forget some names.
Okay.
Which they did all these the FT calculations, and I think the band structure is calculated and see how this evolved with the twist angle.
Yeah. Okay. Yes. Thank you.
Right. It's great. I think that's so far all the questions we've had for today. Let me stop here in this side the streaming for now. And to thank all, I think all in all, it was like 85 of you came in.